Hello everyone, my name is Ertuğ Karamatlı and I will be presenting our work entitled MixCycle, Unsupervised Speech Separation via Cyclic Mixture Permutation Invariant Training. This is a joint work with my co-author, Serap Kırbız. Supervised speech separation has been very successful recently. In supervised methods, the loss function is defined between the estimated sources and the reference sources. However, there is an important downside. In order to have good performance, these methods require large datasets and are usually trained on synthetic datasets that are created by mixing isolated speech recordings. These mixtures may not represent real-life mixtures well. On the other hand, unsupervised methods can work with real-life mixtures that are recorded with a single microphone because they don't require access to the isolated source recordings. The challenging part in unsupervised methods is that defining a loss function between the estimated sources and the input mixture itself, because we can't access the reference sources. In this work, we explore novel ways for unsupervised separation. Here is our neural network model architecture that we use in both the baseline methods and proposed methods. Xi plus j denotes the mixture of the ith and jth sources. This mixture signal is transformed into magnitude and phase spectrograms by an STFT operation. The magnitude spectrogram is fed into the separation network, which is a Kohn-Tasnet model, but a different model can also be used. The network produces time frequency masks that are ensured to add up to 1. Finally, a differentiable inverse STFT operation is used to arrive at the estimated source signals Si hat and Sj hat. As a supervised baseline, we use permutation invariant training. In PIT, the input to the model f theta is the mixture Xi plus j. The permutation matrix P is used to select the best permutation that attains the lowest loss function value between the model outputs and reference sources. We also consider the dynamic mixing of reference sources to have a strong baseline. As an unsupervised baseline, we use mixture invariant training. In Mixit, the model input is a mixture of mixtures. In other words, the sum of two different mixtures, xi plus j and xk plus l, for example. The binary mixing matrix A is used to find the best match between the remixed model outputs and reference mixtures in the loss function. At test time, only a single mixture is supplied to the mixed model. This means that only two of the outputs will be relevant and the other two will not be relevant. This causes the over-separation problem, where parts of the source signals get spread out between the model outputs. Also, it is not trivial to find the two relevant outputs out of 4 outputs when reference sources are not available in an unsupervised setting. Our first proposed method is mixture permutation invariant training. Here we use a challenging proxy task to avoid the overseparation problem of Mixit. In MixPit, we have a mixture of mixtures input, similar to Mixit. In contrast, we no longer have 4 model outputs. Instead, we have only 2. The permutation matrix P is used to find the best match between the model outputs and reference mixtures in the loss function. This is similar to PIT, but we compare mixtures instead of sources in the loss function. At test time, this model circumvents the overseparation problem by having an equal number of model outputs and underlying sources. There are some interesting things going on in the MixPit loss function. There are 3 different output mixture pairs the model can possibly produce because we assume each source is statistically independent of each other. The model can output any combination of sources, such as xi plus k hat and xj plus l hat. The important observation here is that whatever the output combinations are, there are always matches in the loss function, as you can see highlighted in red and blue. For example, let's look at the first possible output pair. We have 2 permutations in the loss function. In the first permutation, we have I is matching, J is matching, K is matching, and else matching. You can see that matching source indices are listed here. In the second permutation, there is nothing match because all of these are different. But this doesn't matter because pit-loss function selects the best permutation, which is the first one. Let's look at the second and third output pairs. So as you can see, we have always two sources matching. And we have 4 here. So we can say that this allows the model to learn to separate two sources because we always have at least two sources matching in the loss function. Our second proposed method is cyclic mixture permutation invariant training. Here we employ our first proposed method, mixPit, as a building block and apply it in a cyclic fashion for continuous learning. In MixCycle, first the mixtures are fed into the teacher model f theta prime, and we obtain source estimates sj tilde and sk tilde. We then use these teacher model estimates to train the student model f theta. We cycle between producing source estimates and using them to update the model parameters. The teacher source estimates that start as noisy copies of the input mixtures transform into accurate estimates of the sources when the training is complete. Inspired by MixCycle, we also propose a blind evaluation method that estimates SISNRI without requiring access to reference sources. We take a train model f theta hat and use it to produce estimates of the reference sources. Then we generate new mixtures using the estimated reference sources originating from different mixtures and separate them once more using the model. We find the best match between the model outputs and estimated reference sources to calculate SISNRI. We evaluated the baseline and proposed methods based on scale invariant signal-to-noise ratio improvements. We compare our proposed methods to both supervised and unsupervised baselines. Although MixPit successfully circumvents the overseparation problem of MixIt, we observe that its performance is not better than MixIt. However, when it's employed in a continuous training method, as in MixCycle, it outperforms MixIt and achieves a similar performance to the supervised method PTM. We also observe that training on the 5% of the dataset obtains a similar performance to training on the complete dataset, which shows the data efficiency of MixCycle. Thank you very much for your attention, and you can find our code on GitHub.